Check out my new 3-page paper on the Jacobsen Epoxidation.
Wow, what an interesting reaction. Want to help me teach it to my students?
Sure.
The Jacobsen epoxidation is a chemical reaction that produces a single enantiomer when creating an epoxide out of an alkene. Jacobsen published his reaction in his 3-page 1991 paper. This is his paper, and this is Jacobsen. This is the overall reaction, and as shown, the alkene forms an epoxide when reacting with the Jacobsen catalyst.
They can't see me. Did you see my new reaction?
I did, but actually I think your catalyst is a little small. Why don't we use a larger catalyst?
Alright, that's an okay idea. I think mine's still better though.
So the alternate name of this epoxidation is the Jacobsen-Katsuki reaction. While they both worked on discovering the reaction, they ultimately published their findings separately because they disagreed on the type of catalyst that they would be using. While they are both magnesium-5 catalysts, the main difference between them is how the double bond would attach to the oxygen that would later be bonded to it. Jacobsen's catalyst favors a top-down approach, while Katsuki's reaction favors a side-on approach. We will not be discussing Katsuki's reaction very much. We will focus mainly on Jacob's catalyst.
So, Jacobsen, I was thinking of putting one of your reactions in one of the workshops.
That'd be amazing. I'd be honored.
There's just one problem. What exactly is your mechanism?
Oh.
The mechanism of the Jacobsen epoxidation is still not fully understood, but it is likely that a manganese-5 species acts as a reactive intermediate for our catalyst, the manganese-3 saline complex, after it has been oxidized by chlorine bleach or similar oxidant. This allows our catalyst to react with and form epoxides with cis-alkenes. The alkene approaches from above the plane of the catalyst, where the newly attached oxygen bonds to the 2 carbon atoms that previously comprised the double bond of the alkene. The bond between the manganese and oxygen then breaks and an epoxide is formed. The manganese-3 saline complex is regenerated in the process and can be oxidized again to reform the manganese-5 species, allowing for further reactions. There are 3 major pathways that are accepted for the mechanism that takes place in this reaction. The concerted pathway, in which a concerted oxygen transfer occurs between the catalyst and the alkene, leading to the formation of a cis epoxide. The free radical pathway, in which the oxygen is transferred via a radical intermediate and can produce both cis and trans epoxides, depending on the substrate and additives. And the metallo-oxetane pathway, where the oxygen is transferred by a 2+2 cycloaddition with a mangano-oxetane intermediate, leading to the formation of a cis epoxide. Of these 3 possible mechanisms, the concerted pathway is currently the most widely accepted.
Professor Lyer, since there's so many possible mechanisms, I don't think we should do a mechanism problem, right?
I think it would be fun for the students to do a mechanism problem.
That would be absolutely, positively, completely, entirely, emotionally, mentally, physically wrong. Let's do a synthesis.
I heard we were talking about organic metallics. Show me.
Of the 3 mechanisms previously mentioned, the first mechanism, the concerted oxygen transfer leading to cis epoxides, is the mechanism that we would assume to be most likely to occur. This is because the bleach reacts with the Jacobsen catalyst, which allows for the ligand association to occur, causing the manganese to go from an oxidation state of +3 to an oxidation state of +5. This then activates the catalyst, allowing for the epoxidation to occur, where the alkenes come from a top-down approach to form the epoxide. This occurs on a cis double bond. Once the manganese-oxygen bond breaks, the epoxide is formed and the catalyst then regenerates through ligand dissociation, forming a +3 oxidation state, allowing for this Jacobsen catalyst to react again when oxidized. The epoxide that forms is both wedged or both dashed. Okay, so now we're gonna go over an example problem together, and for this problem you need to have a cis double bond in order for the Jacobsen epoxidation to occur. So for this one, we're gonna predict the product if this molecule on the left reacts with both the Jacobsen catalyst and bleach.
Here, let me explain.
The Jacobsen catalyst becomes activated due to the bleach, and then the activated catalyst has the oxygen and the manganese, and the oxygen attacks the double bond, and then the double bond attacks the oxygen, resulting in an epoxide to form. And this can be either wedged or dashed.
Wow, stereochem, my favorite.
Ooh, this is the good stuff.
Now that we have done one problem, let's try a more difficult problem with 2 double bonds. This is the answer to the problem, and we know this because the Jacobsen catalyst only reacts with cis double bonds and not the trans double bond. And when it reacts with this cis double bond, it produces this stereochemistry that is either both wedged or both dashed. Alright, here's a challenge problem. So this is 7R8S cis 78 epoxy 2 methyl octadecane, and it's a sex pheromone from the gypsy moth. Synthesize the molecule from reactants of 6 carbons or less. Pause the video. Come on, I know you didn't pause it. Pause the video. Alright, we're gonna move on. Alright, this is the synthesis that our group came up with. You may have had something different, but that's okay. The first thing our group did was we reacted an aldehyde with a lithium reagent, and this created a long chain and an alcohol in the center of the aldehyde. So to get rid of the alcohol portion, we added acid and then added more acid to get rid of the double bond that had formed. So in the next step, or in the next part of the synthesis, we used another lithium reagent and then another aldehyde, but this aldehyde had a C out on the end. So this made a long chain with an alcohol in the center and a chlorine at the end. So then we used PCC to oxidize and to create the carbonyl, and then we used Wolff-Kishner reduction to get rid of the carbonyl group so that we just have this long carbon chain. We then added this long carbon chain to the triphosphine, and that produced this Wittig reagent. So on the bottom, we reacted the aldehyde that we made in the first step with the Wittig reagent we made in the second part of the synthesis, and this produces the cis double bond that we need for the Jacobsen reaction. So after that, we just use bleach and the Jacobsen reagent to produce the stereochem of the epoxide.